Hello, chemistry students. Here is the last portion of your Chapter 8, Section 3 notes over net ionic equations and predicting the formation of a precipitate. This is just from yesterday because we're going to use this in a couple minutes. This is that balanced equation that we did yesterday of silver nitrate reacting with sodium chloride to produce solid silver chloride and aqueous sodium nitrate. Remember yesterday we did the complete ionic equation. To do a complete ionic equation, we take everything that's in the aqueous state of matter and we break it up into its ions. Remember, we did not break up silver chloride because silver chloride is a solid. So remember, when we do a complete ionic equation, we only break up the things that are in aqueous solution. So, starting today, we're going to start with, again, the definition of a net ionic equation. The net ionic equation is an equation that indicates only those particles that actually take place or take part in the reaction. So when we are writing a net ionic equation, okay, assuming, so again, remember kind of our process here is we have started with a sentence. From our sentence, we went to a word equation. From our word equation, we went to a skeleton equation. And then we add coefficients to our skeleton equation to get a balanced equation. Now we have to include the states of matter. Only when you're asked to do a net or complete ionic equation. From our skeleton equation, we did our complete ionic equation. And now we are going to take that complete ionic equation to a net ionic equation. Okay, so this is kind of the process that we've gone through. So yesterday with our complete ionic equation, we identified the spectator ions. To do a net ionic equation, okay, you cross out or get rid of your spectator ions. Remember, our spectator ions were the ions that were in exactly the same state of matter and kind of symbol, if you will. So they had to be the same symbol, the same charge, the same state of matter. And if they were the same on both sides of the arrow, then we said that they were a spectator ion. The other thing about a net ionic equation is that its overall charge must balance. So let's go back and finish that one from yesterday. So again, yesterday we had a sentence and we took that sentence and made it a word equation yesterday, and then we made it this skeleton / balanced equation. Remember, this was kind of an easy one because our skeleton equation was also a balanced equation. Okay? And then we took everything and we broke apart anything that was in the aqueous state of matter and wrote it as its ions. That's what we have here with our complete ionic equation. Okay, so as a review from yesterday again, the next thing I want to do is I want to identify who the spectator ions are. Remember, these are exactly the same symbol, charge, state of matter on both sides of the arrow. So remember, here's my arrow. So Ag plus aqueous, and over here silver's in a compound, so it's not a spectator ion. Nitrate over here is NO3 negative 1 aqueous, and it's NO3 negative 1 aqueous over here. So nitrate, remember, was one of our spectator ions. Sodium, Na plus aqueous on the reactant side and Na plus aqueous on the product side. So it is a spectator ion as well. And then chlorine, okay, chloride, negative 1 aqueous is aqueous, and then it's a solid. Okay, so our spectator ions I've underlined in blue here. It's nitrate ion and sodium ion. So again, now to get our net ionic equation, we are going to cross out or get rid of those spectator ions. So that means that when I go and write my net ionic equation, I'm going to leave these spectator ions out. So that means to get my net ionic equation, all I have to do is rewrite my complete ionic equation, leaving out the spectator ions. So we're going to rewrite our complete ionic equation without those spectator ions. So our net ionic equation for this reaction that we were working on yesterday is Ag plus aqueous. Again, I still have to have my symbol, my charge, my state of matter for my ions, plus Cl minus aqueous yields Ag Cl solid. Again, the purpose of this net ionic equation is it's telling us that the only ions involved in the chemical reaction that takes place here are the silver ion and the chloride ion to produce this silver chloride solid. The sodium ion, the nitrate ion, they're just hanging around, but they're not contributing in any way, shape, or form to the chemical reaction. So the only parts that are taking place in this chemical reaction are the silver ion and the chloride, producing this solid silver chloride. Now, yesterday when we talked about this, I just told you the states of matter. I told you that silver nitrate and sodium chloride were aqueous. I told you that sodium nitrate was aqueous product and that silver chloride was a solid product. However, now you're going to learn how to make those determinations for yourself. So, again, let's look for a moment at that overall charge must balance part. So this one charge overall balances because I have a plus 1, minus 1, which equals 0. Okay. And then on my other side, I don't have any charge because this isn't a compound. So our charges do balance in this example. All right. How then do you predict the formation of the precipitate? Remember, the definition of our precipitate is an insoluble salt. Salt's just a generic term. I know you think it's something that you put on your food, but it actually kind of is generic for any kind of ionic compound. Okay? So insoluble, remember, means it can't be dissolved in water. So these are, a precipitate is an insoluble salt, and a precipitate results from mixing Whoa, that's a lot of letters in there that I don't need. Results from mixing two ionic compounds, like we have happening in our double replacement reactions. Remember, most times if you're going to be asked to do a complete ionic equation or a net ionic equation, it's going to be a double replacement reactions because you have two ionic compounds reacting. So how do you predict that precipitate? You have to use the rules for solubility, which are on page 227 in table 8.3 of your textbook. You have a spot in your outline to fill in this table in your outline. So in your outline, though, there's a little bit more to it, so we'll kind of take a look at that right now. So here are the solubility rules for ionic compounds. Number 1 says the salts of the alkali metals and ammonia. Well, to use that rule, you need to remember who the alkali metals are. Remember, the alkali metals are group 1 or 1A. And ammonia, this is that polyatomic ion you have memorized, ammonium. All right, so what that means is that these compounds, okay, so salts of alkali metals, so compounds that produce or that have alkali metals in them, and compounds that have ammonium ion in them are soluble. That means that you're going to put AQ for their state of matter. Notice an exception, okay? We have some lithium compounds. What that means is if it's an exception to being soluble, it's insoluble. So for some, okay, lithium compounds, we're going to put solid for our state of matter. Moving on to rule number 2. Rule number 2 says nitrate salts and chlorate salts. Remember, nitrate is NO3. -1. And chlorate you have memorized is ClO3, also a charge of -1. Again, these are soluble, so that means you're going to put aqueous with them. And few exceptions means pretty much if you run across nitrate or chlorate in a compound, it's going to be aqueous state of matter. Sulfate salts for number 3. Okay. So the sulfate salts we're talking about, again, sulfate is a polyatomic ion you have memorized. It's SO4, the charge of -2. Okay, and again, these are soluble, so that means I'm going to put aqueous. And again, though, notice that we have some exceptions. So if this is an exception to being soluble, that means that for these compounds listed here, I'm going to put a solid state of matter. So if it is a lead sulfate, a silver sulfate, a mercury sulfate, a barium sulfate, a strontium sulfate, a calcium sulfate, I'm going to put that it's a solid. Number 4, chloride salts. Right, chloride is just Cl-1. Again, we're saying that they are soluble, so that means they should get an aqueous. Now, again, we have some exceptions here. Compounds of silver, all compounds of silver chloride are insoluble, and some compounds of lead and mercury. So again, what these means are that we're going to put a solid for these. Rule number 5, we have carbonates, which are CO3 -2. Phosphates, that's PO4 -3. Chromates, that's the CrO4 -2. Sulfides, that's S with a -2 charge. And hydroxides, OH, -1 charge. Most are insoluble. That means that these are going to get a solid. Notice our exception kind of goes back to rule number 1. It's saying that the compounds of the alkali metals and of ammonia. So again, we're talking about group 1A, 1 or 1A, and and ammonia, NH4 plus. Okay, so again, they're an exception to being a solid, so these would get aqueous, which is consistent with rule number 1 up here. Okay, so you're going to use these rules to predict, okay, what states of matter things are in. So we're going to look at an example. Our example is, again, our sentence is, aqueous solutions of silver nitrate and potassium sulfate react. So again, the sentence is giving you or telling you here that you don't need to look up the states of matter for silver nitrate and potassium sulfate because it's already telling you that they're going to be aqueous. So again, if we start with our word equation here, right, we have silver nitrate plus potassium sulfate arrow, okay, and this, remember, to predict the products, we have to identify what kind of reaction this is. We know that we have 2 compounds here reacting, and the only kind of reaction where I have 2 compounds is a double replacement. In a double replacement reaction, remember, are positively charged ion swap partners. That means that silver and potassium are going to swap. So silver is going to be one of our products, but now instead of its partner being nitrate, its partner is going to be sulfate. And potassium is still one of our products, but its partner now isn't sulfate, it's going to be nitrate. Now, it doesn't matter to me when you want to look at the states of matter. We already know, so we can kind of put little notes to ourselves, right? We already said this would be aqueous. The problem told us that potassium sulfate would be aqueous. All right, so let's take a look at our rule for silver sulfate. For silver sulfate, we're going to look at rule number 3, which talks about sulfate salts being soluble. But notice, compounds of silver is one of our exceptions. So silver sulfate, when we start to write it, is going to be a solid. Potassium nitrate, again, let's take a look at our rules. That's going to be rule number 2. Nitrate salts are soluble with few exceptions. So this is going to be aqueous. So I've kind of already predicted that. That might make it a little bit easier for me as I write my skeleton and balanced equation. Now, again, I'm going to make sure that I leave myself room to put coefficients in front. So likelihood is when I write this, I'm going to end up having to take up 2 lines. Okay, so silver, these are all ionic compounds. So silver, Ag, plus nitrate, NO3, negative. We know it's aqueous because it told us in the problem. Potassium is a K, charge of +1, sulfate's SO4. -2, so I need to write it as K2SO4, and again, the problem told us it would be aqueous. Alright, so silver is Ag, charge of +1, sulfate's SO4, charge of -2, so it's Ag2SO4, and we already used our solubility chart to predict it was going to be a solid. And then potassium is K. Charge of +1. Nitrate is NO3. Charge of -1, so nothing to do to that one. And again, we already used our solubility chart to say that it was going to be an aqueous solution. So I have my skeleton equation. Now I'm ready to balance it. 1 silver, 2 silvers. I need a coefficient of 2 in front of silver nitrate. 2 nitrates, 1 nitrate. I need a coefficient of 2 in front of potassium nitrate. 2 potassiums, 2 potassiums, 1 sulfate, 1 sulfate. This is now a balanced chemical equation. So here's that balanced chemical equation again, just so that it's easier for us to look at. Our next step in an effort to get to a net ionic equation for this is we have to do our complete ionic equation. Remember, in our complete ionic equation, if it's an aqueous state of matter, I'm going to break it apart into its ions. Now, one thing that's different here is this one has some coefficients in it. So remember, this coefficient is going to apply to both silver and nitrate. And this coefficient here is going to apply to both potassium and nitrate. And I have this subscript here, which means I have 2 potassiums, which is going to impact us when we break this apart into its ions. So our complete ionic equation, I have 2 silver nitrates. So that means I'm going to have 2 silver ions with an aqueous state of matter. I'm also going to have 2 nitrate ions with an aqueous state of matter. So when potassium sulfate breaks apart, it's going to have 2, because of that subscript, it's going to have 2 potassium ions, but only 1 sulfate because it just has 1 sulfate. Okay, so that's the reactant side. Our product side, again, we don't break up the silver sulfate, so I'm just going to leave that as it is. Again, that coefficient in front of 2 in front of potassium nitrate means I'm going to have 2 potassium ions, aqueous, and also 2 nitrate ions, aqueous. So that's my complete ionic equation. Now, to get my net ionic equation, I need to identify my spectator ions. So notice silver is not in the same state of matter on both sides of the equation. We go from aqueous here to being solid here, so it's not a spectator ion. Nitrate, however, is exactly the same on both sides of the equation, so nitrate will be one of our spectator ions. And notice that potassium is exactly the same, so potassium is going to be one of our spectator ions. Sulfate is not. So again, if you're asked to identify the spectator ions, you have 2 choices. Okay, I don't care which way you do it, just make sure you do one way or the other. So I can say that my spectators are potassium ion, and nitrate, and so I can use their names. I just have to make sure for my metal that I use the word ion. Or, okay, you can write their symbols. So you can say it's K plus and nitrate. Doesn't matter to me. So now I'm ready to do my net ionic equation, and remember, to do that I'm going to leave out those spectator ions. So to get my net ionic equation, all I have to do is rewrite my complete ionic equation, leaving out my spectator ions. So my net ionic equation for this one is 2Ag plus aqueous plus SO4 -2 aqueous produces Ag 2 SO4 solid. So remember our second rule about net ionic equations was that they had to have an overall charge that must balance. So let's kind of take a look at this one and make sure that that is true. So again here I have 2 positive ones, that's a positive 2 charge. I have a coefficient of nothing, so that's a 1, negative 2, so that's a minus 2. Plus 2 minus 2 gives me 0. On my other side, again, I have a neutral compound that has no charge. So we have made sure also that this is balanced in terms of charge. As long as you make sure your atoms are balanced, your charge should also be balanced. So that brings us to the end of Chapter 8 altogether. Your homework is on page 228, numbers 28 through 31. I will tell you that in our notes, every single time we did a net ionic equation, we did a complete ionic equation first. Some of you have probably noticed a pattern that exists. If you know that pattern and see that pattern, you don't necessarily have to do a complete ionic equation. So for example, in 28 and 29, it says write a balanced net ionic equation. If you can do that without writing a complete ionic equation first, you're welcome to do so. When I go over the homework, I'm going to do complete ionic equations every time just to help the people who are struggling with this. But if you see a pattern, then you can go from your balanced equation to a net ionic equation without a complete ionic one. Have a good day. Talk to you later.